You can refer to me.
So we had the equilibrium point, which was the non-trivial one. So there was a bunch of trivial ones like 1, 0, 0, 0, 0, 1, Gates pointing them out. But the one of interest was this one, so red. So I should start doing this. When I denote equilibrium points, I'll put a star on them, so you know they're different from regular points. So it was 1/3, 1/3. And we computed that the eigenvalues, or rather I computed the eigenvalues. 9 of you gave me different eigenvalues, which are all wrong. But it's okay. We got one eigenvalue, which was I over root 3, and the other one was the conjugate, so minus I over root 3. And we stopped at this point, because any time so far that we've been trying to analyze stability of equilibrium points, we've always relied on looking at the real part of the eigenvalue, so whether it's positive or negative. Here the real part is 0. And if it was just one of them that was 0, it would be okay. But in this case, we have 2 0 eigenvalues. So remember, we have real. So we cannot use, so this is, I should actually write some of this down. So we cannot use the Hartman-Goldman theorem because we have a 2D center line. So we have no way of using the eigenvalues to determine the stability problem. And I told you that this actually has, in the two-dimensional case when this happens, it has a special name. So it's not called a saddle, source, or sink. In this case, it's called a center. And why is it called this? It's called this because if this is your equilibrium point, let's say here, then you have a series of concentric circles. Or, in other words, stable orbits around the equilibrium. So, as these type of centers are what we call stable, but not asymptotically stable. And what is the difference between stable and asymptotically stable? Anybody?
In the long term, one is stable whereas the other is not.
Almost. In the case of stable, we just have orbits that are stable around the equilibrium point, but they never approach, they never become into the equilibrium point. They never tend to the equilibrium point. Asymptotically stable, eventually you have something like this. So you'll start off with orbits around it, but each concession one goes, spirals in, and eventually reaches the equilibrium. So that is the difference between stable and asymptotic. So this never approaches the equilibrium point. It will get very close to it, but never go to it. This will eventually reach the equilibrium. So that is the difference.
In terms of the center, how stable is it?
Extremely stable. Actually, there's a word for it. It's called Leoponostic. And this is what I wanted to try to prove to you, but it's actually quite difficult to do. The proof, so I'll just sketch it like outline it for you. Proof of stability in this case, when you cannot determine it by the eigenvalues, involves what I said before, which was finding these Leopold. So very quickly, how would you do this? First, if you remember what we did was, we said pick a domain. So pick some domain, your choice. But importantly, that contains the equilibrium. Then the second step is to pick a function. Call it b of vector x. So it's a multivariable function. So in this case, it will be b of x1, x2. Then once you pick this function, you have to do a bunch of things. First, you must show that at the equilibrium point, so in terms of 1/3, 1/3, this function is 0. Your choice. Then once you show this, then you have to show that b of x is greater than 0 on b, or on, did I call this at b? I just called it, let me label the domain D, just to, this domain I will call D. So you must show that the function is strictly positive on D. Then the fifth thing is you must show that dv by dt is less than or equal to 0 on D. Now, here's the complication. If dv by dt you find is less than 0 for all points on the domain, then we call this asymptotically stable. Then the equilibrium point, x star I should say, is asymptotically stable. If you are not able to show that it's strictly less than 0, and the best you can do is show that it's equal to 0, then you just say it's stable. And if you can show that your function and domain that you choose satisfies 1 through 5, we call that a strict Lyapunov function. Now, it's not possible to find a function for this case, the center case, because centers are not asymptotically stable. So you will not ever be able to find them. In theory, that means that they are stable. I should be able to find this, but it's impossibly hard. I tried all weekend. It's very hard. Okay. The question is because you see Lyapunov's theorem, it does not tell you how to find these functions. As with most math theorems, they tell you the result, but they don't actually tell you how to get the result you want. So it's completely arbitrary. So there are always candidate functions you can try. And like I said, it's not trivial. Because picking this domain that contains 1/3, 1/3, okay, fine, you pick some of the neighborhood that contains this point. But then you have to test all these things, and every step of the way you would trip up. If you go back and change your domain slightly, because it's kind of hard actually. But some candidate functions that typically one tries, is something like bx1, bx2 is equal to x1 squared, let's say, plus x2 squared. It satisfies certainly over any domain, it's positive. It's 0, well, this is where I should be careful. I should have actually picked x1 minus 1 plus x2 minus 1. So, it's positive, it's 0 at my equilibrium point. But here's where the problem comes. dv by dt is equal to 2 x1 minus 1/3 times x1 prime plus 2 x2 minus 1/3 times x2 prime. x1 prime, x2 prime we wrote down from before. Those are just the differential terms. It's very difficult to show that this is less than or equal to 0, actually, over some domain that contains 1/3, 1/3. So this function will not work. So you have to keep trying different functions is what I'm trying to say. And eventually you'll give up. Another one I tried was something like log of 1/3 x1, x2. which is also 1 over 9. See, I'm forgetting that. So this is 0 at x1 equals to x2 is 1/3. It's positive for a certain domain. The derivative will be negative for a certain domain. And then it will not work at all. So if you keep trying different functions, different sets. Yes?
The 9 times x1
1 over 9.
Sure.
Yes, because x1 equal to 1/3. Oh, you're right, it should be 9. Yeah, 9. So I mean, you try different functions and they'll satisfy some of these properties, but they'll not satisfy others. You have to keep increasing your domain. So it's hard to do like this. So I gave up and did a numerical solution. But it is stable. Centers are always stable. Maybe one day I'll be able to find one. Usually I'm quite good. I couldn't find a function that worked for this. I don't know why. Okay.
So
That's
actually finding there the minimum of the
Yes,
function.
yes, the strict minimum. That's right. Yes.
So if you're finding the minimum, well, it's an energy function, but it's
It could be any type of function. In physical context, the orthogonal functions are always energy functions. So I just kind of gave away the answer to your bonus question. Oops. You should have asked me in private. Okay, no, it's okay. It's very arbitrary what the function can be. It can be anything. So, and the domain can be anything too.
but must it look like one of those functions? Or
No.
is it best that it looks like one of those?
Oh, no. These are just typical ones you try that seem to work in 90% of cases. So why does the first one work? Because it's a positive definite function. So quadratic forms, it's a completely quadratic. They're always positive, so that's a good thing because you can fix it so that it will satisfy the first two properties. Log functions work similarly because log of 1 is always 0, and you can always fix the domain. But it's very arbitrary. There's a biggest point of frustration. So if you cannot find one, maybe there are users that can try and find it. I don't know. Maybe I should just give it one exam question. For your final exam, like 50 marks, find the orthogonal function. Maybe. But anyway, so you can kind of see it. I wrote this in. I forgot my HDMI cable, so what I had to do is record my screen and put it on YouTube. So pretend I have my Mac here. So I should start animating. Yeah. It will pop up. It should. Yeah. Any second. So the red circle in the middle is our 1/3, 1/3, 1. I did it in 3D, so you can see the full system. The red circle in the middle is 1/3, 1/3, 1/3. And you can start to see these stable orbits that form around. I'm going to change the orientation. Yeah. Yeah, sorry about that. Okay, there. So you can see it, the orbits, the solutions to the system, they never hit 1/3, 1/3, 1/3. But they continuously stably go around it. So I do agree. So no matter how hard you try, no matter what initial condition you have, it doesn't matter. It will never hit that point. It will go close to it, but it will never hit. So it's the center. So they're stable. The orbits never crash into the equilibrium point. But it's not as important. And so on. So I think I plotted like 1,000 different solutions for this. With random initial. So I think yeah. Yeah, so you can see. They never go to 1/3, 1/3, but they continuously form circles. So, well, that was for the next one. I'll leave it. Okay, so everybody saw it's stable, but it's not as impossibly stable. I think it's the same idea with, yeah, I will not give away your bonus question anymore. It's kind of overrated. So it's stable, but it's not as asymptotically stable. So what does that mean? That means that I'll put that animation on Moodle so you can play along. So this means that the point x1 star, x2 star equals to 1/3, 1/3. And because of our constraint, x3 then must also equal 1/3 as well. If you remember, since x3 star then is equal to 1 minus x2 star minus x3 star, this means that x3 is also equal to 1/3. So we have a stable point that all the orbits approach in terms of these circular orbits. 1/3, 1/3, 1/3. Which means that even though it's not asymptotically stable, it's still a Nash equilibrium. And what this means is that 1/3 of the population chooses rock, 1/3 will choose paper, and 1/3 will choose scissors. And you know this is what eventually happens in all rock, paper, scissors games. Unless you play a stupid strategy. What the point of this is basically saying is that it doesn't make sense to predominantly pick a strategy, right? Because if your approach is going to be, I'm going to play rock 100% of the time, then your opponent will know that and will just pick paper. You'll lose each time. But if you randomize your strategy such that 1/3 of the time you pick rock, 1/3 of the time you pick paper, and 1/3 of the time you pick scissors, but that's what everybody else is going to do too. So that's why nobody will approach this 1/3 state, but you just will keep bouncing back and forth. And that's what happens in rock, paper, scissors. Apparently this has some biological relevance too, but I couldn't be bothered with it. Something to do with mutations or something. Okay. I'm not interested in biology. Are there any biology majors in this course before Okay, I have to make sure. I don't want to put anybody off. And that's why my next example is also an example from biology. I will end with the nice physics one, actually. The last example will be from cosmology. So you'll see. Let's solve it. Any questions about this? No. So, impress your friends with game theory. You can do a lot, actually. We did really 2 fundamental examples. You did the prisoners development, rock, paper, scissors. There's other ones too. But
is there a way that we can find examples and their solutions online? Practice?
for what?
Practice.
Is this not good enough practice?
It's never enough.
It's never enough? That's sad. That's sad. No, I mean, these examples are actual kind of results. I mean, I can give you some fake dynamical systems that you can work out, but what's the fun in that? But I will post it.
Could you answer this result? I don't know much about it. You did it last time.
It's much longer, but it's the same. Because in that case, you'll have a bunch of stochastic differentiation. You just doing numbers. So it will eventually reach this point. Because you'll have repeated oscillations. That's what you mean, right? So in my phase portrait, oh no, I have to go in 3D now. Okay, I'll pretend this is 3D. Okay. So let's just say this is 1/3, 1/3, 1/3. So we had a bunch of these periodic solutions, right? And let's just say that's 1/3, 1/3.
That's what it was reminding me. That's
Right.
what I saw it.
So eventually you approach, but really if you break this down, there's no time. But if you plot out time explicitly, you just get a bunch of oscillations. Right? That's what you mean. So it's just you'll get the same result. But it's Monte Carlo is always the last resort because you have to do like millions of iterations.
Yeah.
But it's the same. Okay, any questions about this? Besides the off-topic wanting more practice questions?
Yeah.
Monte Carlo is fun. All the bankers use it. But they have no idea what they're doing. No, I mean, much of quantitative finance is done in Monte Carlo.
So we end up with stuff like 2008.
Oh, I can tell you stories about that. 2008, the financial collapse was a combination of,
People not knowing what they're doing.
which are the MBAs, and then combination of assuming everything is normally distributed, which is the only thing that business majors understand. I have to control my comments.
Yeah, it's just like recording.
every keeps, no, it's okay. It's fine. Okay, so example 2. This is going to be a much more involved example. Every example I will do now will be more involved than the previous one. So, this is what we call infectious disease modeling. Is it 2 L's? 1. 2 L's.
Your eyes.
Always figure.
The Google mathematician, good luck.
But in North America, it's not like. Okay, so why does dynamical systems come into play? It turns out that the spread of certain infectious diseases, like measles or malaria, or one of these things, can be modeled by a dynamical system or dynamical systems. And the simplest model of this is called the SIR model. S-I. Why is it called this? So I should make this point. Your math department has like 1,000 people working on infectious disease modeling. And I have opinions about why that is true. But I also must silence my voice on this as well. No, actually, it's, they do a lot of it, but it's like a lot of people doing the same thing. So I don't understand. Like you see, it's...
Expecting a different answer.
I know, I don't understand why. He said a few things. So why is it called SIR? It's because these are functions of time. And what do they mean? They mean this is the population that are susceptible to the disease. Then you have a fragment of the population that's been infected. And R is the fragment of the population that has recovered. So you break up a population in terms of a susceptible category, an infected category, and a recovered. Oh, that's next.
You should probably put an umbrella court on top.
All right. And then first, so with any model, we make a bunch of assumptions, which are practical in some cases, but often it's just a mathematical simplicity. So one of these assumptions, so assumption number 1, is that you assume that the population is constant. So nobody dies from this disease being infected, and there's no new births or anything like that. So you assume that the population remains constant. Or maybe, okay, that's too complicated. So in other words, S plus I plus R prime, so d by dt of this whole thing is 0. Now, in the SIR model, which is the simplest version of this disease modeling, we make one key assumption. In addition to this, the key assumption in this model, so I will do the simple model first, then maybe on Wednesday I will relax this assumption. So the key assumption is what? It is that once an individual has recovered, he or she cannot be reinfected. Which is actually not bad of an assumption. There are many diseases that work like this because you become immune to them. So examples are measles, mumps, smallpox, other ones. So that's our key assumption. And of course, how do you write this down. So that's one assumption. Then we also have to make one more assumption. The other assumption is that the rate of transmission of the disease is proportional to the number of encounters between susceptible and infected individuals. So that's the key, two key assumptions. So what does number 2 mean in letters? In Greek letters? It means the following. So in other words, what we say is that S prime, and prime I mean d by dt, right? You know this. S prime is equal to minus some number, we call it beta, S prime. And of course, beta, I assume, is just some positive parameter. Which is the rate of transmission. So this side will denote this. And we assume it's some positive parameter. So this is the first time in this course we've done differential equations with the parameter. Now, remember, so S and I are functions. Now I've thrown in some pre-parameter to complicate the life a little bit. Okay. And we make one more assumption. The rate at which infected individuals are recovered is proportional to the number of infected, which is also a semi-reasonable thing to it. So at the end of the day, you get the following SIR equation. You get 3 equations. So the first one I've already written down. S prime is equal to minus DSI. You get another equation which tells you the dynamics of the infected population, so I prime, which is equal to VSI minus this constant B times I, and you get a third equation, R prime is equal to VI, where in this case, B and B or beta are just positive numbers. So B or nu, but I will just write B, because I cannot tell the difference between B and nu in my own writing. So B is just the rate at which infected individuals recover, and beta is the rate of transmission. But this is a dynamical system now, which has a bunch of non-fixed numbers, like in the game theory cases, now has these arbitrary parameters. So it's going to complicate the life of the bit. But notice something about this differential equations. There's no R in the first two. So number 3 is actually a free equation. It's an extra equation. It's an auxiliary equation. The dynamics are really only covered in the first 3. So this is what we call an auxiliary equation. Because there's no R in one. R is not in one. And you can also see this in the following sense. I assume that the population was constant. So this means that R plus S plus I is equal. So we have another constraint, like we did with the game theory case. I can use this constraint also to eliminate one of the variables. But it's your choice. So our dynamics are completely covered by these two. Any questions so far? So now what do you do? So there are nonlinear equations because of the SI problem. So it's hard to solve. So we must use our methods of analysis that you become quite good at, I hope. Okay. So, analysis. So what is the first thing I do when I'm encountered with a dynamical system? Yes. So step one, find the equilibrium. And that those will occur when the right-hand side is equal to 0. So keep repeating this to yourself. So in other words, we have two equations. Minus beta Si is equal, and the equilibrium points are going to be obviously S star, I star. So find S star, I star, such that minus BSI is equal to 0, and where beta Si minus BI is equal to 0. Any ideas? It's really easy to solve this system. There's only 0, 0? So when we find the equilibrium points, remember, we don't want to touch the parameters. We just want to know when S and I, which S and I solve this. So 0, 0 is one of them, but in general, what is the...
They're equal.
Say it again?
They're equal.
No. What if I said I equals to 0? Just I.
Oh.
Does it work? So irrespective of what S is, I equals to 0 seems to be equilibrium point for all values of S. So I actually have an infinite number of equilibrium points for this. I have a line of equilibrium. So there's only one solution to this, namely that I is equal to 0. If I is equal to 0 here, you get 0 is equal to 0. If I is equal to 0, you get 0 minus 0 is equal to 0. So irrespective of what beta is, irrespective of B is, irrespective of what S is, I equals to 0. So what, geometrically in my two-dimensional plane, what is special about I equals to 0? What does it signify?
The line is all equivalent line.
The SS. Yeah. In other words, the entire positive, because we're assuming that these are positive quantities. The entire positive S-axis, which is I equals to 0, contains equilibrium points of the system. Very cool. So every single point along the S-axis is an equilibrium point for I equals to 0. And this state signifies what when I equals to 0? How many at this state infected people do we have? There's no infection. So there's no disease in this special equilibrium state. So the question is now, what is the stability property of this point, or these points? And that's now, how do I do that? What is step 2 after I found the equilibrium points? Jacobi. So it's the same steps in every situation. Again and again. Okay. So remember, step 2 is Jacobian because we want eigenvalues. And how many eigenvalues am I expecting for this system? 2, right, because it's a 2-dimensional. Okay. So the easiest thing when you're doing the Jacobian is to call this first function f1 and call this f2. Just like we did before. Because remember, the general form is x prime is equal to fx. So x1 prime is equal to f1, x2 prime is equal to f. In this case, x1 is s, x2 is s, and f1 is this, f2 is this. So then the Jacobian matrix is what? It's partial f1. So maybe I'll write it on just right now. df1 x1, df1 partial x2, partial f2 partial x1, partial f2 partial. In our language, okay. So what is the first entry? What is partial f1 partial s? Negative beta I. Yes. Keep going. What's the second row? The first row, second column. Yes. The third one is going to be beta I and beta s. Okay. So that's the Jacobian matrix for any equilibrium point. So now to find the eigenvalues, what do? I substitute in my mind. So this is generic. So I found my Jacobian. Now step 3 is to sub in my equilibrium point, which in this case is just I equals to 0. So what happens? We get the Jacobian. So if I is equal to 0, this is going to be 0. You get minus beta s 0 and beta s minus b. So that is the derivative matrix at this point, or at these points. So now I can find my eigenvalues. And now you see the complication. So my eigenvalues now will depend on beta and b. So hence the stability will depend on the signs of these free parameters. So that's step 3. Step 4 now is to compute eigenvalues. Thank you to Poincaré once again. No idea how you do that.
Any more?
All right. But then I also need more paper. I should keep the binder there maybe. So what are my eigenvalues? Well, if you remember, as usual, we solve determinant of lambda or lambda minus k just like this. So in this case, that is determinant minus lambda minus beta times s, 0, beta s minus b minus lambda. And now I must compute the determinant of this. Equal to 0, which implies what? You get minus lambda times beta s minus b minus lambda is equal. So what are my solutions to this equation? Very good. So remember, I want two eigenvalues. So the first one is just going to be 0, and the second one is going to be beta s. And as I said, it's not a problem when you just have one zero eigenvalue. It's a problem when there's two. So in the case when you have one zero eigenvalue, you just look at the sign of the other. You ignore it. And you can do this. I will not go into the theory of why this is possible. But, so, what type of equilibrium point do I have if all the eigenvalues have non-zero real values? What is that called? Hyperbolic, right? In the case when you have just one zero eigenvalue, such a point is called normally hyperbolic. And this theory, which was, I believe, founded by German mathematician Holbach, allows you to ignore the zero eigenvalues. So you just study the stability of the point by looking at the non-zero point, which is this one. So now you see, is it a sink, is it a source, or is it a cell? It depends now on what the signs of these parameters are doing. It's a little bit more complicated, but not really. It's just now some algebra with inequalities. In other words, So look at sine of lambda 2 is equal to beta s. Now, there's a bunch of cases. Okay. If lambda 2 is 0, which is the bad case of the two-dimensional center manifold, this will occur when beta s is equal to b. We can have a sink if my eigenvalue is negative, so when lambda 2 is less than 0, and that is when beta s minus b is less than 0. Okay. And of course, this means that s must be between 0 and b over beta. Because remember, s, I, and r are going to be positive numbers. So I must bound the lower one by 0. And it can be so this is going to be a sink. You can have a source if lambda 2 is positive. And we just reverse the sign. So this means that beta s minus b is greater than 0, and that means that s must be greater than 0. Okay. So that's how you do this type of analysis. You see, you can have a sink or a source now, depending on what the signs of b and a are. It was not like this before because we just had fixed numbers. So we always got a distinct answer. Are you going to always a sink, a saddle, or source? Now it depends on what parameters you feed into this. And remember, these are parameters, it's your choice. Whatever you want, whatever. But ideally, you pick these from the data that's available. So you do some type of regression that gives you both these numbers on based on the data of infectious diseases. Okay.
Any name for number?
Sorry?
Any name for number 1?
Oh, yes. So in this case, you have 2 zero eigenvalues. And you have a center manifold. So you must actually do a bit more analysis for this. It's not complex, so it's not going to be a center or something. That's the problem.
So it is a center number.
Sorry?
It is a center number.
Oh, yes, yes, because you still have 2 zero eigenvalues. So I will just, yes, so I wrote that. So in other words, in summary, what we can say about this SRO, and you have 2 minutes left to do these evaluations, which was stupid on my part. You said should have worked. So in other words, so the line I equals to 0, which corresponds to 0 infected, is a local sink if 0 is less than s less than 0 b, and it's a source if s is greater than b. So there's something happening between this transition when you have less than b over b and then greater than b over b. The stability of the system changes fundamentally from a sink or a source. So we have to analyze this a bit more detail, which I will do on Wednesday. And the basic idea is the following, is that when you have 3 parameters, this leads to the phenomenon of what we call bifurcation, which are the most interesting part of dynamical systems. And bifurcation really means a change in stability of the system. So I will continue with this on Wednesday, but now you will have to oblige me with these course evaluations. Any questions about this? So that you see now, it's the same thing over and over again. I solve for my equilibrium points, I find the eigenvalues, and I just look at the signs of it. And sometimes you'll get center manifolds, and you must do some more analysis, like a numerical solution or a Beyond-Function or something. But it's the same steps, again and again. The remarkable thing that you should take away is that all the theories in math and science boil down to this. So this is a fundamental language of nature, is dynamical systems. But anyway, okay, so